Section 2.3, using Venn diagrams to study set operations. Let's look at our Venn diagram here on the left. It's a rectangle with two overlapping circles labeled A and B. And within these sets A and B, as well as our rectangle, we have some regions labeled 1, 2, 3, and 4 using Roman numerals. If we look at our first region, region 1, we see that this would contain elements that live in set A, but not in set B. So these are elements in set A, but not in set B. Let's compare this to region 3 over here. These are the elements that live in set B, but not in A. And I skipped that region in the middle, or region 2, because those are going to be the elements that live in both A and B, right? They fall within both the red and blue circle. I guess I should have made that in purple, right? Like mixing colors. There we go. So region 2 represents elements in both sets A and B. Or like we learned in section 2.2, this would be the intersection of sets A and B. Now we have one more region on the outside, region 4. And remember when we first started talking about Venn diagrams, I asked you not to confuse this outside region with the universal set. The universal set is all of our regions, so everything within the entire picture, rectangle or circles. This region 4 is just the elements that live outside of our circles A and B. So these would be elements that are in our universal set, but that are not in sets A or B. Let's try to utilize a Venn diagram to illustrate a specific set. And the set we're talking about now is the complement of A union B. And notice how I read that, the complement of A union B. The reason I said it that way is because that implies to the reader that you want to find A union B first, and then figure out the complement of that set. This would be different than saying something like A union B complement. That may be interpreted like this, where you would ask you to take the complement of B and then union that with A. That's not what we want. We want the union of A and B, and then the complement of whatever that set ends up being. And we're going to shade that region on our empty Venn diagram. So let's start by listing out which regions live in these individual sets. So starting with our universal set. There are 4 regions. Our universal set will contain all of them. If you don't like using Roman numerals, feel free to just write it out with our standard numbers. In set A, I see we have regions 1 and 2. Write down which regions are in set B. That would be 2 and 3. And then in the union of A and B, remember that's everything in A or B or both. So for us that would be 1, 2, as well as 3. Now we want to find the complement of the set we just figured out, which is this A union B. And I can write these all in set notation as well with our curly braces. So if we're looking at this A union B set, which contains 1, 2, and 3, comparing it to our universal set, which has 1, 2, 3, and 4, we see that the complement of 1, 2, and 3 would just be region 4. Now we want to illustrate that on our Venn diagram. And we do that by just shading in region 4. Now, some students can just look directly at this picture and figure out what that shaded region would be. But I do recommend practicing it by writing down the sets like I did on the right, because eventually we're going to get into Venn diagrams that have three intersecting sets, and then it gets a little bit difficult to just look at the picture and figure it out. So it's good practice to write it down. So on your own, why don't you try exercise 2, which is asking you to illustrate the intersection of A and B complement. Notice there's no parentheses here like there was in problem 1. So this is indicating to find set A as well as to find the set of B complement and then intersect those two sets. So pause the video and try that on your own and then come back and check your work. So far, I just wrote down the sets A, B, and the universal set. Let's check if you got B complement correct. So remember, you need to compare set B to the universal set, and you want to take everything in the universal set that's not in set B. So for us, that would be regions 1 and 4. And now we have the sets we need, A as well as B complement, to figure out what their intersection is. Remember, intersection are just where they touch or with what they have in common. So it has to be something that's in both of them. And the only region I see that they both have is region 1. And then we were asked to illustrate this on our diagram. So we would shade in region 1. So again, when you write it out like we did on the right, it almost gives you like a paint by numbers. You figure out the set you were looking for, and then you just go paint in the number that was indicated in that set. Now, both times we've done it, we've ended up with just one region, but sometimes you'll end up with multiple regions. So you'll just paint in every single region that lives in your set. Good job. Let's move on to Venn diagrams with 3 sets. So looking at this picture we have on the right, we can see that we have sets A, B, and C inside of our Venn diagram. And this breaks up our Venn diagram into a few regions, regions 1, 2, 3, 4, 5, 6, 7, and 8. In region 1, these are the elements that live in set A, but not in sets B or C. Notice that A contains the regions 1, 2, 4, and 5. But in regions 2, 4, and 5, they intersect with B or C, which means that they aren't strictly stuck in set A. They happen to be in both. But in region 1, I'm not touching any of my other circles, so everything in region 1 is strictly in set A. Let's move on to region 3. So in region 3, we have a similar thing happening, but with set B. So region 3 are going to be all of the elements that are in set B, but not in sets A or C. And I'm going to skip again down to set 7. So region 7 are going to be all of the elements that live in set C, but not A or B. Then we have these regions between these sets where we have some sort of overlap, right? So we can see region 2. Those are the elements that are in both sets A and B, but not in set C. Similarly, we have region 4. Those are the elements that are in sets A and C, but not set B. And similarly, again, we have region 6, which are the elements that are in sets B and C, but not in A. And then we have this special set in the center, which is region 5. Region 5 contains all of the elements that are in sets A, B, and C. And notice I still have my outside region, which is region 8. And similarly to our Venn diagram that had only 2 sets, this outside region that's not inside any of the circles are going to be all of the elements that are in the universal set, but not in sets A, B, or C. So now we know how to read the diagram that has 3 intersecting sets. Let's move on to doing a problem. Exercise 3, we want to illustrate the set A intersect the complement of B intersect C. So like we did with the Venn diagrams that only had 2 sets, it's helpful to write out what these individual sets look like. So I know for sure I need to know what set A is. So the regions that are within set A are 1, and this time I'm going to use regular numbers in case you're struggling with Roman numerals, 2, 4, and 5. I also need to know B and C so I can find their intersection. Or if you feel strong enough doing these types of problems, you can just immediately jump to writing down what the sets would be within that intersection. If not, though, why don't you just write out each one individually? And then looking at those, you can figure out which elements they both have. So they both have 5 and 6. Looking at the picture, you would have seen that's where their 2 circles touch. All right, but we don't want to find B intersect C exactly. We want to find the complement of that set. So now you need to compare it to your universal set, which has all of the regions 1 through 8. So comparing these 2 sets, my complement is going to contain everything that's in the universal set that's not currently in B intersect C. So I basically just want to exclude 5 and 6, leaving me with 1, 2, 3, 4, 7, and 8. So we're almost there now. We have every set that we needed to find in order to figure out our actual picture. We just need to figure out the intersection of sets A and this new one we just found, which was the complement of the intersection of B and C. So think back to like order of operations. The parentheses are important. So the parentheses around B intersect C told us to find that intersection first, and then that complement on the outside told us to find the complement after we found the intersection. Now we get to look at that entire entity as one set, and we're intersecting that set with A. So I just need to compare these sets. And I want to find the intersection of these sets, or in other words, which numbers do they both have? Well, they both have a 1, they both have a 2, they both have a 4, they don't both have a 5, and now since I'm out of elements from that one set, and I'm doing an intersection, I'm done. So to shade the region that represents A intersect the complement of B intersect C, I need to shade in regions 1, 2, and 4. Any element that lives within this region also lives within the set A intersect the complement of B intersect C. That may have been a little fast, but remember you can replay that part. But now I would like you to try problem 4 on your own. I didn't even draw the picture for you, so you get to draw the entire thing, find all the sets, and shade it in. So pause the video for a few minutes. This might take you 5 to 10 minutes to figure out. And please actually pause the video and try it. Don't just wait for my answer. Remember, we don't have class time together, so it's very important that you spend some time working on your own to check for retention. Okay, so pause the video and then come back and check your work. So I started this problem by drawing the picture again for myself and filling out my different regions. I just used our standard numbers this time. And I also wrote down what is in each set. So in our universal set, sets A, B, and C. Now you can check your work with me. One of the first things we need to figure out is A complement, because we need that set as well. So I'm going to write that over here. And I just compare A to the universal set. I take everything from the universal set that's not in A. So that's going to be 3, 6, 7, and 8. Now I have my A complement and I have B, so I can figure out their intersection. So I'm basically going to mix these two sets together. Look at these to figure out their intersection. So remember, that's going to be the things that they have in common. So I see that they both have a 3 and a 6. So now I know what A complement intersect B looks like. But I need to find the union of that set with set C. And remember, I said that unions tend to be the easiest because you don't need to figure out what matches, you just take absolutely everything you see. So I see a 3, I see a 4, a 5, I see a 6 from both of them, and I see a 7. Now to illustrate this, I just go shade in those matching numbers. So I need region 3, region 4, region 5, region 6, and region 7. How'd you do? If you didn't get it, that's okay. These problems can get pretty tricky, but I promise you with practice you will get better. So if you're someone who tried to just look at the picture and shade in what you thought was right, there's a good chance maybe it didn't work out the way you had hoped. So again, I would recommend taking the time to write out all the sets like I did. If you did write out all the sets like I did, just go check your work to see which numbers you may have missed or misplaced. De Morgan's laws. For any two sets A and B, we have these two rules. The complement of A union B is the same as the intersection of A complement and B complement. And similarly, the complement of A intersect B is the same as the union of A complement and B complement. So notice what happens is the individual parts end up getting the complement and the union turns into an intersection, or vice versa, the intersection turns into a union. And we're going to prove that these are the same using these Venn diagrams. So basically, we're going to shade them in and see if the two pictures match. Let's start with the one on the left, and I'm going to have this picture represent A union B complement. And we're just proving the top law. So this is this law. We're going to show that we end up with the exact same regions shaded in. Okay, so I first need to know what's in A. So the regions that are in A are 1 and 2. The regions that are in B are 2 and 3. So the regions that are in A union B, I have to take everything I see, right? Because union means take all of it. So that would be 1, 2, and 3. But I actually want the complement. So you got to compare it to the universal set, which has 1, 2, 3, and 4. A union B complement, therefore, would just be region 4, right? If the union has 1, 2, and 3, then the only one that's not within that already would be 4. So I'm going to shade in region 4. So what that means is any elements that live within region 4, you can also say that they live within the set, the complement of A union B. All right, let's look at A complement intersect B complement. Again, we know that set A contains 1 and 2, so that means that A complement would contain sets 3 and 4. We know that B contains sets 2 and 3, so what would be in B complement? Well, that would be 1 and 4. Remember, it's everything that's in the universal set, but not in the set we're looking at. And we want to find the intersection of these two sets. Intersection means the stuff they have in common. So when I look at A complement and B complement, the only number I see in both of them is 4. So I will shade in that region. And what we notice from our Venn diagram is the exact same region was shaded in, which proves that the complement of A union B is the exact same region as the intersection of A complement and B complement. Or we can say that De Morgan's law holds. And you could repeat this exercise for the second law and you would end up with 2 matching pictures. If you take the time to work out this second law the same way that we did the one in purple, you should end up with these 2 pictures. And if you, in your note packet, do the work like I did by writing out all the sets underneath, like sets A and B and everything you need to find to show where you got these 2 pictures, I'll give you an extra point on your note packet, okay? Cardinality of a union. Let's draw a Venn diagram illustrating the sets below and then use the diagram to find the cardinality of A, B, A intersect B, and A union B. So recall from our last video that the cardinality is the number of elements in your set. So first thing you want to do is you want to fill out this blank Venn diagram to match what elements are in these sets. So I'm going to call this top one A and this one on the right B. Remember, the whole thing is U. Inside set A, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. And inside set B, I have 6, 7, 8, 9, 10, 11, 12. Some of these numbers are in both sets, like 6, 7, 8, and 9. So in our picture, we need to determine where we should write those numbers first. Since they're in both, we should draw them in the intersection in the middle. So again, it says, notice that 6, 7, 8, and 9 are in both sets when drawing this diagram. Now you can write the leftovers from each set in just their part of the circle. So just in what we used to call region 1, I'm going to write down the numbers 1, 2, 3, 4, 5. And in the region we were calling region 3 earlier, I'm going to write the leftovers 10, 11, 12. Now, none of my numbers fell into that outside region that we used to call region 4, and that's okay. That just means everything in the universal set happens to be in either set A or B. Now that we have our picture, we can count our cardinalities. Looking at set A, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 elements. Looking at set B, I have 1, 2, 3, 4, 5, 6, 7 elements. Looking at the intersection, I have 1, 2, 3, 4 elements. And looking at the entire union, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 elements. So maybe you notice, if not, it's okay, but we could figure out the number of elements in your union by adding up the number of elements in set A as well as the number of elements in set B. But if I just do that, I end up counting the 6, 7, 8 in the middle twice. So if I just subtract off that intersection one time, then I've gotten rid of the issue of double counting. When I do that, I end up with 16 minus 14, which is 12, which matches the number of elements in my union. Now we were asked to use the result to develop a formula for the cardinality of a union. Well, we just did that. You can count the elements in each set. So for us, that was sets A and B. And then subtract the elements in the intersection. Or writing it out in a more mathematical way, we can say that the cardinality of our union is equal to the cardinality of our first set plus the cardinality of our second set minus their intersection.